I think. All right. So, guys, today's presentation is from Aman Chadha. Aman Chadha is a senior tech lead manager in generative AI at Apple. Before that, he was in Amazon Web Services, as you can see here, and he is. You can see, excuse me, publishing in prolific uh, you know collaborators and publishing in a lot of generative AI topics, uh, including some of these publications include some of our students. So he's been a fellow with the AI Institute and also with Sipana Saha, who was a Fulbright fellow here until recently. Um, but by and large, it deals with a lot of Gen AI issues, and alignment appears to be his one of the uh, you know core areas of interest. But many other things you can see here, uh, low resource languages and such. It so happens that at Apple, so Aman, you're going to present something. Is that generally relevant to Apple or totally different?
It's totally different. So I'll be presenting on-device machine learning today. Yeah.
Okay. All right. So clearly, there's one more topic that he's working on. So let's be hearing. Thank you, Aman, for accepting this, and we'll get started.
Thank you so much for the intro, Dr. Shade. I'm gonna start by sharing my screen. Let me know when once you guys can see it. Are you able to see the screen?
Yeah.
Okay. All right. All right. All good now, right? You can still see
Yeah.
the screen. Okay,
Yeah.
perfect. All right. So the topic for today is going to be model compression for on-device AI. So we're going to be covering a whole bunch of different methods that essentially help you take a trained model and deploy it on device, right? So what does it take to go from a model that is ready, model that has been tested and works well for a specific task or use case, and then once latency constraints or cost constraints or even battery constraints hit, because you're looking to run this model in a privacy preserving way, say on your cell phone for example, or within your browser. So you do not have quite the compute that's available in a typical cloud setup with tons of GPUs. What do you do to get your model in shape, for one of these applications? So that is what the talk is going to be centered on. And on the right, you see a whole bunch of different topics that we're going to cover as part of this talk. So going in clockwise order, we'll start off from the problem statement. I'll formalize what it means to compress a model for on-device AI and why we need on-device AI. Then we're going to talk about an overview of model compression techniques. We'll figure out the lay of the land, and we'll understand the kind of techniques that are available at a top level. And then we're going to delve into each technique one by one and cover it in enough detail for you guys to understand the pros and cons of each technique and what to use when, right? So we're going to cover quantization, we're going to cover knowledge distillation, we're going to cover pruning. And these are the three biggest areas in on-device AI, and you guys might have heard of some of these in various different contexts. For example, Llama, the four that was recently announced, it's the Scout and Maverick models are a distilled version of the Behemoth model, right? Which is the biggest 405 billion parameter model that's currently being trained by Meta. So distillation was done in that case for Llama 4 and Llama 3, 3.1, I believe, 1 billion and 3 billion variants. The SLM variants of Llama 3 were also distilled from bigger models, right? So that is the norm right now in the industry to create an SLM going through knowledge distillation, right? So we're going to cover that as well as part of the three big areas: quantization, knowledge distillation, pruning. And then we're going to touch upon some other, allied areas as well, like quantized low rank decomposition and adaptation. I'm going to also touch upon, things beyond compressing a model. So KV caching, which is something that every provider out there, whether it's, a cloud provider, Amazon or Google or, Microsoft, or any kind of, even lower level provider, a startup level provider also uses KV caching. That is the norm right now in terms of inferencing models. So it's widely accepted in the field. So we're going to be talking about that as well. And then we'll touch upon lightweight model design, what it means to design a model from scratch with the lens of deploying it on device as the end result. Um, and lastly, I'll touch upon some further, reading papers that you can go through if you'd like to dig deeper in this area. And I'll also share a link to the primer that I have that covers all of these topics in, next level detail, right? So today we're going to cover these at a relatively higher level, but I've got next level detail in my primer as well. So that's going to be the agenda or the structure for today's talk, right? So with that, and towards the end, I'm happy to take questions, or if there's any questions in between as well, feel free to pause me. So yeah, let's get started with that. So first off, we're gonna set up and formalize a definition for on-device AI, right? So here's the entire problem statement, right? The models that we have today, right now, they with scaling laws, we've seen that models do better when there's enough of a parameter count, which leads to an increase in their expressiveness and their ability to tackle a whole bunch of different tasks with reasonable levels of accuracy. So scaling laws have told us to go for bigger models, and the field is pursuing that, and we're seeing better performance on a whole bunch of different benchmarks. Um, but the challenge with these models is that they demand a significant amount of compute and memory, especially if you're looking to deploy a model, in the trillions of parameters right now. A whole bunch of these leading state-of-the-art models have gone ahead from hundreds of billions of parameters to now trillions of parameters. How do you come up with the kind of compute and memory that's needed to offer that level of performance on something that is, a local device like a cell phone, for example, right? So the edge devices, edge here is basically the term that the field uses to indicate devices like phones or augmented reality headsets or even IoT systems, right? Could be even your thermostat looking to pattern recognize, how you want your temperature when you're at home in various, months of the year. Uh, all of these devices have limited compute, right? Most of these devices have a system on chip inside which has a dedicated IP to be able to run, neural models, right? So phones definitely have that. IoT systems could be running these same models on a lower end neural processing unit within the device, or could still be using the CPU. But at the end of the day, they have limited compute, right? Orders of magnitude less compute and memory compared to, the GPU based clouds, right? So power budgets are another concern, right? If these are battery operated devices, you can't be running a face recognition model, on your iPhone or Android device all the time, right? So that creates additional challenges. So these are some of the biggest concerns, but there's also another big angle to using edge models, right? Which is essentially privacy. How do you ensure, especially in scenarios like healthcare, for example, that data isn't transmitted beyond the four walls, right? It doesn't go to, the cloud, which is typically owned by a different provider and could even be in a different country, which means, HIPAA regulations and, GDPR and a whole bunch of these things then come into play. And this not only destroys privacy, but it also introduces additional latency, right? It also introduces the need for, connectivity, right? So all of these challenges are what have motivated the field of on-device AI to blossom. So privacy, latency, offline operation are key areas where on-device AI lends itself pretty well. Um, and whether it's LLMs or whether it's diffusion models, it's targeted task specific models. all of these can be packaged in a form that makes it easier for us to run them on device. So that is what we're going to be covering today. That is the entire problem statement of on device AI, where the goal is essentially to minimize model size and compute cost. And the way we do that is by using a bunch of compression techniques, which we're going to be covering today. And obviously, at the same time, as we're bringing down the model size, we want to make sure we're not losing on accuracy. And the end goal for all of this is to enable low power and privacy preserving and low latency compute directly on end user devices. So that is the entire problem statement of on device AI. Now, with that, now that we've established what it means to, have on-device AI, and why do we need on-device AI, we're gonna now go from the what to the how, right? What are some of the model compression techniques that we see in the field? So we're gonna touch upon a quick overview of each one of them. So there are, like I mentioned earlier, quantization, knowledge distillation, and pruning are the three leading approaches. And there are other approaches that have come up recently that the field is still adopting, and using them in conjunction with some of the three big approaches as well. So you can combine bunch of these approaches together too. So they are cumulative in certain cases, and obviously the end effect might not be directly cumulative. You might not be stacking the benefits of one approach and the other on top of each other, but most of these are you can definitely stack, and then the final benefits or the end result is empirical. So running experiments is what will basically give you the best signal to understand if, say, quantization and knowledge distillation put together, what kind of gains you're seeing in latency, and is there any impact on performance at the same time. So a lot of this is empirical. For example, for quantization, the idea is to reduce precision. So if you when we train a model, if it's trained in single precision, it typically uses float 32 values for each of its weights, right? As well as the so going from 32-bit, you can go to a int 8 representation. So that's just 8 bits. So you just saved memory and compute by a factor of 4. Now, compute is a bit of a different story. Memory definitely was saved by a factor of 4, because earlier, where it would take you 32 bits to store each of the weights and activations, now you're using 8 bits, right? With compute, the story is a little more nuanced, where every GPU that rolls out from NVIDIA or from any of the other providers, AMD or otherwise, dedicated cores within the GPU to be able to run operations at a certain level of precision, right? So, for example, a couple of years ago, NVIDIA announced Tensor cores. So that was a big innovation where they were able to deliver, lower levels of precision on the GPU with reasonably high performance. So with every GPU generation, for example, the latest one being Blackwell from NVIDIA, we're seeing that they are able to give us reasonably high levels of performance at very low levels of precision, say even 4 bits, 6 bits, or 8 bits of floating point. We're able to, run operations at such lower levels of precision with very low latency and reasonable levels of performance. And the latency part is what they seek to optimize, right? As they reduce the amount of precision, the idea is that you can make optimizations in hardware where it's able to fuse operations much easier and carry out matrix multiply and add operations, which are the most common set of operations in any kind of neural network, relatively quicker. So that is the entire thesis behind quantization, to be able to lower the level of precision, but at the end of the day, do it with way lower latency and offer reasonable levels of performance, right? So that is quantization. Pruning and distillation take a different angle to improving efficiency for neural networks. They remove redundancy, and for in case of pure pruning, where you identify neurons within the entire neural network that aren't contributing as much to the end result, to the output of the model. So we'll talk about structured pruning and unstructured pruning as well in the later slides. And knowledge distillation, the entire idea behind that is to use a teacher-student setup where you're distilling results from a teacher by sending over not just the hard logics, the final predictions that are being made by the teacher to the student. You're also sending the probability distribution of at the output of the teacher over to the student. So the student learns from two signals. It learns from soft logics as well as the hard logics. The soft logics being the probability distribution. So knowledge distillation, this is the main reason knowledge distillation has shaped the field recently, as far as small language models, SLMs, are concerned, pretty well, because that is the best way to take a bigger model and then distill it down to a smaller model and have it learn from two signals, right? Soft and hard logics. Whereas if you would directly train a smaller model, you can only offer it hard logics. You can only give it the next token that it needs to predict, right? As it's being, say, pre-trained on unstructured data like Wikipedia. But when you're distilling, you can give the student model more signal than just the next token. You can give it a probability distribution across all of the tokens as it's predicting the next token. So that's knowledge distillation. And again, we'll go into detail, in upcoming slides. But that was pruning and knowledge distillation, and we've got low rank decomposition, which is you guys might have heard of low rank adaptation, LoRa, which is very common in the field to fine tune models right now in a parameter efficient way. There are quantized versions of LoRa. There are versions that basically help us adapt these models, in a quantized manner. So the weights of the base model in certain cases are quantized, depending on what kind of specific type of quantized LoRa you use. There are a bunch of different proposals. There's Q LoRa, there's QA LoRa, for example. So bunch of different methods here that we'll touch upon in the later slides. And lastly, we've got lightweight design as well, like I mentioned earlier, which is the entire idea of designing these neural networks with the end goal of deploying them on device, right? So how do you come up with a small network in the first place that will let you deploy this on device with reasonable performance and low latency? So that is basically work that we do from the start to be able to come up with a model, rather than take a bigger model and then somehow get it in shape for the end result of on device AI. So these are the key areas that we'll be covering today. So this was meant to be a quick overview, and now we're going to delve into each of these areas in detail. All right. Now, next up, we've got quantization. So, like we discussed earlier, the entire idea behind quantization is to map both the model weights and activations from high precision to lower bit width, right? So, and there are a lot of different proposals as far as quantization is concerned. There's no one type of quantization, right? So if you look at the figure on the right, you'll see that there's dynamic quantization, there's post-training quantization, there is quantization aware training, and we'll talk about each one of them on this slide. But there's a these are standard traditional approaches in the field as far as quantization is concerned. And quantization, by the way, the entire idea stems from signal processing theory, right? So this is nothing new for the area of specific to the area of neural networks, but has existed in the field of signal processing for several decades. So the field has essentially leveraged the entire idea of quantization and applied it towards neural networks, and then has come up with specific proposals relating to neural networks as well. I have a bunch of new techniques, that apply specifically to neural networks in an upcoming slide. So we'll talk about that as well. But at a top level, there's a bunch of different methods, and the entire goal, like I discussed earlier, is to reduce model size and computation cost significantly, while ensuring that accuracy is maintained to reasonable degrees. And the way we typically do it is we come up with a plot of performance versus latency. And then we basically, for each level of quantization that we choose, we conduct experiments, come up with latency numbers, and then that that could go on your x-axis, and then correspondingly on your y-axis, you'll look at the level of performance that you're seeing, and then you figure out a level of performance that is acceptable on that performance versus latency graph, and then you choose the level of quantization that is needed to achieve that level of performance, right? So that is how trade-offs are made as you deploy these models. But looking at the specific types of quantization, um, so there's post-training quantization, there's quantization aware training, and there's dynamic quantization, right? So apart from dynamic, the other two types of quantization, post-training quantization and quantization aware training, both are static in nature. And here's why, right? So with dynamic quantization, as you're running a neural network, you're basically going to quantize your weights and activations on the fly, right, based on data that is being collected, calibration data that the module uses. And PyTorch has a bunch of different modules that you can use. A lot of the details, implementation details, including code snippets, are in my primer, which I'll link towards the end of the talk. But we've got APIs right now within PyTorch that we can use for any of these standard types of quantization, these three in particular. There's a lot more newer methods, which I'll be touching upon in probably the next slide, which aren't as easily available, but there's code bases for each one of them at this point. So, with coming back to dynamic quantization, as your model's running, it's able to figure out the right it implements quantization on the fly, which is why it's called dynamic. There is no pre-processing or work that's done beforehand to quantize weights, right? This is all done during inference time at runtime. So that is dynamic quantization. Post-training quantization is a static form of quantization where you've got a model that has already been trained and is ready for a particular task, runs well on the cloud, and you've tried it out. But now you have to basically come up with a method to be able to deploy it on device, right? How do you bring it down in size, for example, right? And by the way, on device could also mean running it locally on your laptop, for example, right? So that's use case as well. Uh, is there a question or?
No.
All right. Okay. So post training again, the idea is you got a model, and the idea is to now get it into shape for on device use, right? So what we do is we basically run the model through representative inputs to collect outputs that we see on these particular inputs, and we call that a calibration set. And that basically is what is used to understand the distribution of the weights and activations, of the activations in particular. And we do a similar thing for the weights, where we understand what the distribution of the weights is. And this is the information that's needed to be able to quantize it, right, at runtime, after it's trained, uh, trying to figure out which level of quantization would work best in this case, right? Going from, say, float 32, do you take it to float 16? Do you take it to float 8? Do you take it to int 8? Do you take it to even lower levels of precision that Blackwell, NVIDIA's latest GPU, now supports, right? So that is the decision that's made once you have a trained model, and then running post-training quantization as a step after the model is trained. So that is PTQ, and QAT is another type of quantization, which, and the way it differs from the others is, as the model is being trained for the first time, we basically inject fake modules within the training ecosystem, and PyTorch has these modules handy. So all you have to do is call these APIs, which basically quantize the model, with the lens of using it for on-device AI as the end result, right? So it's carrying out computation at lower levels of precision while it's being trained, to make sure that once the model is fully trained, the level of accuracy and performance that we could have seen with, a regular model, a non-quantized model, versus the quantization of our training model is similar. So these are fake quantization modules that are introduced during training to simulate quantization, and that is how QAT operates, right? So you've got three major options within quantization, and the idea is to figure out what fits best for your use case by running empirical experiments and understanding what makes the most sense. Now, the challenge here is that depending on what your neural network is doing, it could be a transformer decoder, which is typically the architecture that's used for all kinds of LLMs right now. Could even be an MOE model, which is again very much utilized for today's LLMs. Could be a state space model, could be even a convolutional neural network or a vision transformer, many different types of models and architectures. The challenge is that the operations within the model, each of these operations, right, whatever it takes to go from input to output, all of those have to be supported at the level of precision that you're looking to have the device run the model at. So what I mean by that is, for example, if it's a convolutional neural net, we need to make sure that the device is able to run convolutions at, say, a lower level of precision, say float 16. If you were to, go from single precision float 32 to half precision float 30, right? So each of these operations have to be implemented at lower levels of precision. So you've got to write CUDA kernels, if it's NVIDIA GPU, for example, at that level of precision for each operation, which is why you need a whole ecosystem or a library around this, which PyTorch offers in most cases, um, to support these operations at different levels of precision, right? So that's one thing. There is a hardware dependency in this case, so that needs to be considered as you're deploying the model. But the end result of doing all of this is you've got large memory savings. Inference becomes faster, low latency, and the accuracy loss. If you've chosen the right point in that performance versus latency graph, you're gonna see minimal accuracy loss. And the cons is obviously, because you're deriving this model from the main model, there could be edge cases or areas where you see instability or you'll see accuracy drop significantly, especially with certain layers that are doing a particular form of computation, say with state space models. If the model running some of those critical operations, the particular layer, if the lower precision variant of that particular layer leads to a significant drop in accuracy, your overall output, right, your end result is definitely going to be suffering as well in terms of accuracy compared to the original model. So the depending on the nature of the operation that you're quantizing, the nature of the layer, the end result can be drastically different. But the ecosystem is pretty strong at this point. This is widely adopted in the field, and it's standard in the field right now to quantize models. Even when we run a whole bunch of these large models right now on the cloud, in some cases we run quantized versions. So float 16 is very commonly used. That's half precision, even as we load, for example, a llama model on the cloud, right? So quantization is definitely widely utilized in the field. All right. And then this slide basically covers, some part of what we discussed earlier. So there's dynamic quantization, there's post-training quantization, and quantization aware training, like we discussed. And these are more of the traditional methods, that have come up, over the last decade or so. There have been a bunch of new methods that have come up to, for quantization, which I'll cover as well. But just to give you guys a quick overview, for dynamic quantization, you're quantizing activations on the fly during inference, and this gives you great flexibility. You don't have to do any work beforehand. You take an off-the-shelf model, and you're able to dynamically quantize it, so there isn't as much overhead. But the cons is that it's, for certain architectures, for example, for convolutional neural networks, we don't see great levels of performance with dynamic quantization, right? So that's one thing to keep in mind. Depending on the model architecture, you'll have to switch to a different kind of quantization. Transformer-based models actually do pretty well with dynamic quantization, is what we've seen. Now, looking into post-training quantization, what we're doing here is gathering a calibration data set, like we touched upon earlier, which is basically the outputs of the model by sending in representative inputs, right? Inputs that are going to be commonly seen across all the kinds of different use cases that you want your model to support. So that is the calibration data set that we gather, and based on that data set is how we quantize the model, right? Based on the distribution of that data set, right? The values, the range of values, for example. So this is fast, and you don't need to retrain the model. You already have a trained model, and you're looking to post training quantize it. However, it might lead to some accuracy loss, especially with sensitive layers. So that needs to be figured out. Layer by layer analysis needs to be done. But otherwise, this is very much utilized in the field, because you don't need to retrain a whole model from scratch. Once you have a model trained by, say, a frontier lab, you can run post training quantization on it. Last one's quantization aware training, which is pretty different compared to these two, because as you're training a model from scratch, you're simulating quantization. So this cannot be applied if you already have a model available that is pre-trained by, say, a frontier lab, right? So that is one thing to keep in mind. And the way it works is by injecting fake quantization modules, which is how it simulates the entire process of quantization as the model is being trained. This does give you the best accuracy, though, as you'd imagine, it's the best bang for buck, because you're training the model from scratch with the idea of deploying it in a quantized manner, right? And it handles low bit precision pretty well. However, the most obvious con is that you have to fully retrain a model from scratch, so there's compute costs in the picture. But if it's a mission critical scenario, say it's healthcare, or an important decision that the model is going to take at the end of the day, this is the most common choice, QAT. All
Aman,
right.
do
Yes.
question here.
Yes.
So what order of magnitude of hardware are we talking about on a device? Like a high-end workstation in, 100 gig drive, or are you talking about like a 100 core type machine?
Yes, that's a good question. All of that depends on the kind of compute horsepower you have on the GPU, or whatever IP it is that is running the model at the end of the day, right? So even if the CPU is, say, 100 cores, like you just said, it's not going to change much, because unless the CPU is running the model, right? So we'll have to look into the specific IP first, right? Which is looking to run the model in cloud deployments. Obviously, we've got GPUs. NVIDIA GPUs are the most common. But in on-device deployments, we typically do not have GPUs running, models. We have specialized neural processing units, NPUs. Every company has a different name for their the neural part of their system on chip that powers their, phones, for example. For lower end IoT devices, it could still be a small CPU running the model. But the idea is, at the end of the day, the thumb rule is that if you're not able to satisfy your latency requirements, where it takes your latency or power requirements, where it takes you, several times the amount of time to generate an output. For example, if it's a interactive system like a voice assistant, right? If you trigger a voice assistant, it can't take you more than 300 to 400 milliseconds to get a response. Otherwise, it just feels unnatural, right? So if it takes you way longer than that, then you need to look into one of these methods and, quantize it for the device. Same thing with the battery devices, right? Phones, for example. If you're going to be running big models on it, you will still get a response from the device. But the challenge is, if it drains your battery within 10 minutes, then it's not worthy of pursuing, right? So that's typically the analysis that we do to figure out if we really need to head down this path or not.
So Tim
Does that
Cook's got
answer?
you. Is that the answer?
Uh, I,
Apple's got
I,
you.
Sorry, I can't see the audience, so might not have a lot of context. But did that answer your question?
Yes, sir.
Perfect.
I was
All right.
I was making a joke of whether Tim Cook actually had you covered at Apple.
I see. I'll spend a little time at the end for questions as well. But I got a couple of things to cover, so going to race through some of these slides. So, like we just discussed, right? There's standard methods for quantization. We just talked about them, but there's a whole bunch of new papers that have come up in this area. And there's a bunch of labs. There's Song Han's lab at MIT, for example, that has been doing a lot of work in this area. Activation aware weight quantization, AWQ. The first one on the slide came from that lab, and it's one of the more commonly deployed options. Smooth quant, GPTQ, AWEQ, bunch of different options, right? So let's touch upon each of them quickly, one by one. So AWQ, what it does is that it does weight scaling per channel, instead of doing it at a layer level or at a tensor level. So that was one thing that they did. But what they did was they used activation statistics of the model, which are essentially the products at each layer, at the output of each layer of the model, as a guiding principle to scale their weights. So that was the novelty that they proposed, and this led to strong accuracy for LLMs, which is why it's a very commonly deployed quantization techniques. If you pick up a Llama 3, for example, you'll see a bunch of different AWQ options online on Hugging Face that you can use. So this is a kind of a favorite for LLMs, if you will. No retraining required in this case. And in terms of the cons, this does have a higher pre-processing cost because you're running inputs through the model to generate those activations. And then you're using those activations to scale the weights. So there are a bunch of different steps and hoops to go through before an AWQ model is ready to use. But otherwise, for edge GPUs and NPUs, like I was just talking about right now, answering the question, neural processing units, NPUs as well as GPUs, AWQ is a very commonly used method. So that's one of the newer variants that have been proposed. Similarly, we've got smooth quant, we've got GPTQ and AWEQ. Smooth quant is basically the idea of smoothing the activation outliers. So what it does, it basically generates a whole bunch of different activations, similar to what AWQ does as you're sending inputs to the model. But then what we do is we identify the outliers, and then we smoothen them out using a fine scaling before we quantize it. Hence the name smooth quant, right? And this has led to stable quantization and more robustness, right? Because you're targeting just the outliers in this case by smoothing them out. But in certain architectures like convolutional neural networks, we see lower levels of performance for smooth quant. And for deeper models, GPT and Llama and a whole bunch of different LLMs, we do see great levels of performance with smooth quant. And a whole bunch of these methods, you'll see the common thread binding them is that they're targeted towards LLMs, right? The traditional methods, as we saw earlier on the prior slide, they were methods that formed the basis of the field of quantization. But a whole bunch of new proposals and papers that we're seeing in the field are targeted towards LLMs in this case, just because there's a lot of good momentum there. And GPTQ is another one, which basically minimizes quantization error. And the way it does is that, and this is the novel portion here, it uses the second order gradient updates to be able to minimize that quantization error. So that's the novelty here. Again, no retraining required. So it's a post-training quantization method. It's got PTQ in its name. PTQ is what we discussed in the prior slide too, right? So you can have an off-the-shelf model. You don't need to retrain a model. Otherwise, the GPTQ offers great levels of performance on LLMs as well. AWEQ is yet another one, uses activation weight statistics similar to AWQ. And then it balances the channel scales instead of directly targeting weight scaling, which AWQ does. So in a way, this is a little bit of a variant of AWQ. But per layer you'll have to calibrate the scaling, which is one of the biggest cons here. But the one of the biggest use cases with AWEQ is mixed precision quantization, right? So if you want to run a model, the individual layers of the model at different levels of quantization, right? So one layer could be more important than another, and then you can run it at higher level of precision. So that is where AWEQ shines. So yeah, these were some of the newer proposals. And then that concludes quantization. And then now we're going to get into knowledge distillation. Knowledge distillation, like we discussed earlier.
Aman, what is the uh, uh, what is that weight activation? What is that? How is that determined?
Let me go to the prior slide. You were saying weight activation?
Yeah, go back one slide.
Yeah, this was the last slide we were on.
No, no, one before this.
This one?
It's not showing you, right?
Yeah, it's not sure.
Do you
Yes.
see?
AWEQ, I think is what he was asking about.
Yeah, if you go into the quantization,
One slide prior here.
yeah, this is the one.
Uh-huh. Sorry, what's the question again?
Uh, so what is the um, wh- what are the issues in activation rate? I mean, is it or how is it tied to the tokens?
Yes. So the weights are basically the parameters of the model. That's the model itself. But the activations are essentially the weights multiplied by the input. The input is essentially the tokens in this case, right? So once you discretize the token, create an embedding out of it, and then multiply the weights with that embedding, the input, that is how you get to the activations. So that's how they're related to the input tokens.
But how do you know that this is a higher weight versus lower weight? How does it translate into the weight per se that is meaningful in any way?
So the when we train the model, quantization assumes, unless you're doing quantization aware training where there is no model, but most forms of quantization otherwise assume that you have a model already that's trained. So the weights are calibrated uh, during the training process using backprop. The model's fully trained, so you have the weights available, and these are the weights we use to basically multiply with the inputs, at every layer. So at say at the very input layer, at the start of the model, you're going to be taking the token, discretizing it, coming up with an embedding, and that embedding gets multiplied, matrix multiplied by the weights, which are the ones that are already trained, and that basically leads you to the activation for that layer, and then so on and so forth for subsequent layers.
Hmm. Yeah.
So in this case, the weights are ready for us to be used, right? They are all the model is already trained, so we have the weights. Unless you're using quantization aware training, in which case you're training the weights as well live, so that you're going through the entire model training process live. All the other forms of quantization assume that the model is fully trained and the weights are ready to be used. Does that answer the question?
Yeah, yeah.
Perfect. Just going back to knowledge distillation. Yes. So the idea behind knowledge distillation is to have two models, the teacher model and the student model. Um, and the teacher model is a pre-trained model, all right? So you already have a model that's available. And to give you an example of Llama 4, so we've got the Llama 4 behemoth model, 405 billion parameter model. So it's nearly, half a trillion parameters that is already available as a teacher. And what is being trained in this case is a student, which is what Llama 4 Scout and Maverick which were released earlier this year. That's essentially the process that they went through, right? And the way we do that is that we basically have the student match the output of the teacher. So we match it with two different lenses. We look at the soft labels of the teacher, which is essentially the probability distribution of the teacher at the output of the teacher. And that goes in as a training signal. So this is explicitly part of the loss function for the student. And we also have the hard labels, the actual output that we expect, if it's a supervised data set or even self-supervised corpora, right, where you have the next token that you're looking to predict. That is your hard label, right? The actual output that you want the model to generate. So these are the two signals that are essentially fed in as input to the student via the loss function. So the loss function has two components, soft labels and hard labels. So we do a KL divergence, for example, over the soft labels, and we run a standard categorical cross entropy loss as what we use for every training every LLM out there, over the hard labels. And these two components are what are used to train the student model, right? And the way this is done is by passing in some training data to both of these models, both the teacher and the student models, and that essentially generates the distribution at the end of the teacher, the probability distribution, and the probability distribution at the end of the student. And that, along with the hard labels like I mentioned earlier, basically go into that loss function. So that is the entire essence of doing knowledge distillation. And like I mentioned earlier, this is one of the most common methods to train small language models. You take a bigger model and then you train a smaller model by distilling the bigger model, rather than training the smaller model directly, taking instantiating a way smaller model, 1 or 2 billion parameter model, for example, and then training that from scratch, right? Because in that case, you do not have the soft labels from the teacher that will help, give enough signal to the student. You only have the hard labels, right? If you were to train a small language model from scratch. So this is why the field right now has converged to using knowledge distillation as it trains, for example, a smaller version of Llama, or even training Gemma, for example, right, and distilling a smaller Gemma variant from, much bigger model that Google has. This is the process that these labs go through. Now, knowledge distillation has a bunch of different types. There's offline distillation, there's online distillation. There is, with offline distillation, that's the setup we just discussed. You've got a fixed pre-trained teacher. And with online distillation, what you're doing is you're training both the teacher and student jointly, where you basically have training data going through the teacher and student, and at real time, the teacher is generating the predictions as it's being trained. So that's online distillation. But otherwise, there's a strong, performance level that we typically see here, way better than training a small model from scratch, like I mentioned earlier, and great levels of efficiency, right? Now, when we run inference, we're only running inference on the student model, so we do not need to have the teacher model be deployed at all. So essentially, there is no inference overhead once the setup is done, distilling. Um, Now, when do we use this compared to, say, quantization? When you can retrain a model from scratch, which is the student model, and the goal is to retain the performance levels of the teacher as much as possible in a smaller model. So that is the use case for knowledge distillation. And next up, I just want to do a time check. Do we have 10 more minutes or so, or did I get the timing right? I just want to confirm how much time we have because we have a bunch of slides to cover.
Yeah, I mean, certainly till 15 past the hour and maybe up to 20 maximum.
Okay, okay, sounds great. Yeah. Um, Next up, we've got model pruning. That this is yet another variant of trimming down or compressing models, where pruning, essentially, the theory behind pruning is to come up with the set of unimportant weights on neurons. And the way we do that is we use certain forms of statistics, and I'll talk about that too. And the end goal is to reduce the computation memory use for pruning for the model, right? So that is the entire hypothesis behind pruning. And the way we do that is we employ two different types of pruning. We have unstructured pruning, which basically tackles individual weights, right? So there is no structure to the kind of neurons that we select. It's just at an individual weight level. And the other option, right, the other variant of pruning is structured pruning, where we basically tackle the entire filters or channels within the model at a time. So those are the two different variants. With unstructured pruning, we do see high levels of compression, but on the other hand, we do see irregular sparsity. So it's very difficult to make a conclusion if a certain, say, layer or a channel was not useful, at all as the model was being trained. And this does bring down hardware efficiency, right? Because you cannot skip an entire layer or a filter or channel altogether as you're running a model. So that is one of the biggest challenges with unstructured. Now, with structured, we do see good levels of compression and efficiency, compatibility with existing hardware as well, where you know that a certain layer wasn't quite useful for a representative set of inputs that would pass through a model. So in that case, we can skip that particular layer or channel fully, because you can it'll essentially be a sparse layer where most of the weights there are zero. So that is the entire idea behind structured pruning. Sorry, was there a question? I'm hearing something.
Yeah, yes. Am I audible?
Yes, I can hear you.
Okay, so my question to you, I had like two questions, but I was sitting back, so I couldn't ask. But I'll start with the question
Sure.
from the current slide. Is
Mhm.
how well does like the hardware implementation of a Brew network go? Because as far as I'm aware, when you have a sparse network,
Mhm.
sparse network just feeds those values as zeros, right? So it's still like
Right.
the hardware multiplier will still have to multiply something with a zero, and which is not efficient. And how do you save like latency, for example?
That's a good question. I can tackle this one and then we can go to your next one. The hardware does not multiply if there is a zero. That is the entire optimization here. If it's because the hardware knows that anything multiplied by zero is zero, it is hard coded in the hardware to skip the entire process altogether. So it saves cycles significantly.
So that's hardware dependent, right? Like let's say if I have a GPU kernel, I can implement it there, but sometimes a specific hardware, let's say edge hardware, doesn't necessarily do that. Am I wrong?
Uh, no, it's not at the software layer, not at the kernel layer. Within the hardware, when it sees that one of the operands to an operation is zero, it will skip the entire operation altogether and give you a zero back. So you don't even need to put it into code. It is
Is
optimized at a much lower level. So today's, CPUs, for example, on your chips, this is baked in as part of the hardware logic, right? Even in CPUs, even GPUs, NPUs, that is how they save cycles. If they realize that a certain operation is not worthy of pursuing, it will directly give you an end result back rather than wasting cycles within the hardware to crunch through the numbers and then give you a zero at the end. So which is why that is the entire thesis, sparsity and pruning, to be able to save hardware cycles as it's computing matrix multiplications and adds.
Oh yeah, that's what I was getting at. Like matrix multiplication in sparse network doesn't necessarily decrease the complexity of the overall algorithm. Is what I meant. Like when I said hardware implementation, not specifically like single multiplications.
Yeah,
Uh,
the matrix multiplications are decomposed as small blocks of multiply and adds within the hardware when these models are being run.
okay, but
So
still sparse, right? Still not like optimized in the hardware.
it is fully optimized in the hardware right now. That's which is how these chips are getting exponentially fast, right? If we did carry out these optimizations within the at the lowest levels of hardware, we're going to be wasting cycles, right? Because we're going to be putting in an if condition in code saying if one of the operands to a multiply operation is zero, just return a zero back, right? Rather than doing that, have the hardware basically look at the operands, which it's going to look at anyway as it's carrying out multiplication. And when it sees a zero, it returns back a zero because it knows zero into anything is going to lead to a zero, right? So that's where the entire optimization part comes in. Does that make sense?
Yeah, it does. I was just thinking because if that's the case, anyone like could do sort of an LU factorization, and that would help a lot. Like there are a bunch of multiplication and bunch of zero multiplication in that case, and you will save a lot of memory. But I get your point. And my second question: are you able to take my second question right now, or like should I wait towards the end of the slide?
How about this? I can also send you some pointers about the first question
Okay.
and so documentation that basically says there are hardware optimizations for sparsity. I
Okay.
think that's the entire area that you're interested in, and also I can take us the second question over email as well. And my email on the last slide. I'm just
Well,
concerned about time right now, and I've 40% more of the presentation to cover. So I'm gonna race through the slides, but if there's questions, I'm more than happy to take them. You guys can email
yeah.
me. I can send you some.
Uh, yeah, I'll be happy to get your slides and get more questions and answers.
Yeah,
It's
for
fun.
sure. For
Thank you,
sure.
Aman.
Thank you. So yes, coming back to structured pruning, this is what was utilized for Llama 3 as well. Llama 3.1, 1 billion, and Llama 3.1, 3 billion also utilized structured pruning to be able to bring down the size of the model. So again, a very standard, method in the field that is used as we're, training an SLM, for example. So pros and cons here, looking at the size of the model, obviously that goes to a significant reduction. There's enough of speed gains as well. In terms of cons, the challenge with pruning is that there are various aspects to the algorithm that you need to tune. You need to come up with a pruning schedule and figure out the various thresholds that are needed to tune. And if you prune aggressively, and if those schedules aren't set correctly, in which very this is very similar to learning rates and their schedules that we use to train any kind of neural network model. Those need to be tuned and set correctly, because if you go aggressive there, then that can harm generalization. So you'll see, the model not being able to perform well during runtime, especially in a long tail of the scenarios, right, where there's edge cases and the model doesn't quite do well. So that is a trait of models that have been aggressively pruned. But otherwise, when you need to, when you can retrain and you have compact hardware friendly models that you need to deploy on the edge, pruning is typically used. In case of Llama, it was used in conjunction with knowledge distillation. So like I was mentioning earlier during the start of the presentation, you can couple a whole bunch of these different techniques together as well. That's how it's typically done in the field. So they're not orthogonal. They are orthogonal in that sense, and the benefits might not be stackable exactly, but that is figured out empirically, right? To see what benefit you got from distillation and then pruning, and then a combination of both. But these methods can definitely be stacked on top of each other. All right. And then we've got quantized low rank decomposition. There are two algorithms or two papers in the field that are very commonly cited and used, QLoRa and QA-LoRa, right? And we also use these in a whole bunch of our research, where instead of using LoRa to fine-tune models, we now use QLoRa to be able to fine-tune them in a quantized way, right? So that eases compute costs. You don't need as much compute availability available. So LoRa is the off-the-shelf variant, low rank adaptation, but QLoRa in this case, what it does is it basically combines LoRa with 4-bit quantization of the base model. And for all of the updates, that it's generating, that goes through a 16-bit computation, right? So that's half precision. But the model itself, the base model, is quantized at 4 bits. And the way it does is that it uses something called as normal float 4 quantization, which is a new data type that's introduced by QLoRa, and that this basically enables it to fine tune a 65 billion parameter model on a single GPU with just 24 gigs of VRAM, which is likely an Ampere GPU considering the amount of VRAM that they use. So that's not even one of the more recent Hopper or Blackwell GPUs. So fine tuning becomes way easier, especially if you have a large model. One of the bigger llamas, for example, you can fine tune that easily with just one GPU. So that was the result that QLoRa showed us. QA-LoRa, on the other hand, took one step further beyond QLoRa, and it introduced quantization aware scaling and adaptive rank allocation per layer. So those were the two different novel aspects. And the way it did that was basically by adjusting the rank and the precision at runtime based on the sensitivity and the variance of the activations across layers. So it basically monitored the activations at each layer as the model was running a particular input, and then figured out what the variance there is, and accordingly adjusted the rank and precision. Right, and the rank here is basically the rank of the LoRa adapter that gets generated at the end. So the rank here is variable in that case. It's adjusting that dynamically, and this basically reduces the compute and latency for any of the on-device and mixed precision deployments. So that was the idea behind QA LoRa. I've linked both of the papers on the right, so feel free to take a look. But what we get at the end with a quantized low rank decomposition and adaptation technique is model that is fine tuned in a parameter efficient manner, and offers high accuracy at extreme levels of compression. And this works best when you've got a base model. So you say if you take a llama, for example, and you want to fine tune it on a particular use case, but do not have the compute available to be able to do that, right? And don't have a distributed setup where you've got 4 or 8 GPUs available within a particular node, or spread across nodes even. So with a single GPU, you're able to fine tune a base model, a significantly larger base model, say 65 billion parameters in case of QLoRa pretty easily. So that is the entire selling point here with quantized low rank methods, which is different compared to other methods that we discussed, right? They did not have as much of a fine tuning focus, but this is the most common way in which we're using models right now, right? We're either prompting them or we're fine tuning them, which is why quantized low rank methods have picked up a lot of momentum recently. All right. Next up, we've got KV caching, which is a different method, and uh, this is very commonly used as we run inference of on any of these models. What KV caching does is that it basically caches the keys and values from previous tokens as it's decoding one token at a time, right? As it's going through its auto-regressive loop, right? So as you're running an LLM, you're generating outputs, the next token, essentially, which is what you're predicting. And KV caching stores the keys and values from all of the prior tokens, right? So this basically ensures that you don't go through redundant computation, and you can just use the cache representations easily at every step. And this significantly reduces time complexity, where because each new token only needs to attend to the cached keys and values, right? So which you've already stored and cached. So don't need to recompute that, and that basically gives us an O of n time complexity instead of the n square quadratic time complexity, which is commonly seen in plane transformer models because of the self-attention operation that powers these transformer models. And that brings down. This is a classic, space versus time trade-off in computer science, right? So we're essentially using space to lower the time complexity here, right? So this brings down the latency and compute costs. Um, Now there are hybrid variants of KV caching as well that quantize the KV cache as well, right? Up until now, all of the quantization techniques that we discussed were quantizing either the weights or the parameters of the model or the activations, right? The output of each layer that get generated as an input is thrown into the model. But quantized KV caching is yet another variant where we take the KV cache and we quantize that further, right? So, say if it's a float 16 KV cache, all of those tensors, okay, float 16 tensors, right? All of those tensors as we go through quantized KV caching will basically be represented with int 8 or int 4 in this case, right? So this will fit it with limited device memory. Chunked or dynamic caching is yet another key aspect where you could partition the whole KV cache into different chunks as it's done in operating systems, for example, with virtual memory.
Hi,
And
Aman. Because of the time constraint, can we just do the highlight of whatever the remaining slides are?
yes, and
Just the
I can,
topic
yeah,
definition.
yeah, absolutely. Yes, sir. And I can share the slides as well later,
Yes, I
and
will
we can,
share the slides with everyone.
sounds good.
This is very interesting and in fact, we do have some people from a group here that works in this area, so they will be
Yeah,
particularly interested in following up.
yeah, perfect. Sounds great. And I can take questions over email as well.
Yeah.
So that way, we're but yeah, let me just touch upon the key highlights. So KV caching, those were the biggest aspects. With lightweight model design, the idea is to basically design a model from scratch that focuses on efficiency, right? So there's a bunch of different trade-offs that we can make while we're designing these models. For example, depth width trade-offs are the most common. Do you create a deeper model versus a wider model? Any optimization you can do on the attention stack, for example, come up with linear attention instead of quadratic. A lot of different options, right? And I have a bunch of different architectures here: mobile BERT and tiny BERT, for example, mobile net, efficient net. These are standard models and architectures in the field that have implemented some of these different techniques and made some of these trade-offs to create smaller models. There's also the idea of neural architecture search, which basically automates the process of figuring out what kind of architecture would fit your memory and compute constraint the best. So you can use NAS as well, neural architecture search. So these were the two key areas as part of lightweight model design. And lastly, I've got a list of different papers that we've covered today, all of these different ideas in the field, right from model compression to the basics of model compression to quantization, knowledge distillation, pruning, low rank methods that we touched upon, QLoRa, QA-LoRa, and KV caching and lightweight model design. So a list of papers here, and once the slides are shared, you can easily access these. So that's the idea. And yes, I've got a primer as well that covers a whole bunch of these topics in next level detail. So you can take a look at that. The link is down below. Yes, and with that, this is my final slide. So yeah, thank you for attending the talk. And like I said, my email is here. So if there's any questions, happy to take them over email.
This is wonderful. Thank you very much, Aman.
Thank you. Thank you so much.
Great talk.